Okay, let's go ahead and get started. Last time we started this section just by showing how to derive the formula for what we're going to call the equation of a line. Officially, it's the parametric equations of a line. This is a three-dimensional line, so we have to be able to come up with some kind of formula to tell us exactly what x, y, and z, the points on the line, are. And what we had said was that all we need is one particular point on the line, call that x naught, y naught, z naught, and a direction vector for the line, call that direction vector ABC as its I, J, and K components. Once you know the point and the direction vector, you have everything you need for the parametric equations of the line. And there are other forms of the equation of the line, but we're going to focus just on the parametric equation of the line. And so once you have the point and the vector, then the best way to write it is in this vertical fashion. And these are three equations that describe exactly all the points, coordinates, the x, y, and z coordinates of any point that's on the line. You just take your point, your x naught, y naught, z naught. Oh my gosh, sorry. You take your point, your x naught, y naught, z naught, and you put that as the constant part, and then the I, J, and K components of your vector, you just end up multiplying those by the parameter t. Think about t as your time parameter, and when t is 0, you're at the point that you know, x naught, y naught, z naught, and then t is allowed to be anything positive or negative. T is any real number, and so as you change the t, you'll get a different point on the line. But from our derivation, we had described exactly how to get that equation of the line, and we'll be calling it the parametric equations of the line. Okay, questions? So if I give you 2 points out in space, then you can definitely find the line that goes through those 2 points. There's different ways the question could come at you. Here's that question. I give you 2 points randomly, 5, 1, 3, and 3, -2, 4, and ask for the parametric equations of the line containing these 2 points. We said that we needed 1 point and a direction vector. We have 2 points, so pick either one. And when it comes time for the direction vector, you can go from one to the other in any order, whether you're going from the first to the second or from the second to the first. Remember we said how to find the vector between 2 points out in space? You just take the terminal points coordinates and subtract them from the initial points coordinates. And so if we say the 3, -2, 4 is the terminal and the 5, 1, 3 is the initial, then the I, J, and K components of our direction vector is going to be 3 - 5 for the I, and -2 - 1 for the J, and 4 - 3 for the K. So we have our vector that goes from the first point to the second point. There's no unique way to do this. I randomly chose that direction, and I can go the other direction, and I'm going to randomly choose either of these points. And so when you get the equation, there's no unique way. I might be able to force you to give me the answer where all of you would have the same answer by picking the point for you, like giving you the x naught, y naught, z naught, and then having you figure out the A, B, and C. But for the most part, this is not a unique answer. And so you put the points coordinates down vertically, and then you put the director, the I, J, and K components of the direction vector down vertically. Don't forget to multiply those by the parameter t. So for us, let's just take the point 5, 1, 3, and then -2, -3, 1 are our I, J, and K components of our direction vector. And this is a description for every point that's on that line. You give me a time t, I'll tell you exactly the point x, y, z. Okay, when t is 0, I'm at the point 5, 1, 3. And the way we have it set up, when t is 1, we're at the other point, 3, -2, 4. And then t can vary, be anything between 0 and 1, anything after 1, anything before 0, and you'll be able to get every single point that's on that line. Questions about that? Yeah. All right, sounds great. That's just a typical question. I mean, there's nothing too hard about that. I just want you to get the idea of what we're looking for when we say find the parametric equations of the line. It's a description of all points x, y, and z that are on the line. Okay? All right, great. So then when you have 2 points, 2 lines in space, then, well, remember, think about in 2D. When you had 2D, back on the plane, either your lines were parallel or they intersected. In 2D, remember, the lines either were parallel, they had the same slope, or they intersected in some point, or there was a third option where really the second equation is just a different form of the first equation, and the lines are basically one on top of the other. Let me just emphasize that by having 2 different colors here. Okay, these are the 3 different options you had in 2D. And so now in 3D, we're asked the same kind of setup, what could happen. And so in 3D, we could have parallel lines. And we don't say the slopes are the same because there's no more notion of slope. It's all about direction vectors. And so we can't say that the direction vectors have to be exactly the same as long as the direction vectors are scalar multiples of each other. They don't even have to be pointing in the same direction, just as long as you can say that this vector is this vector times some constant, right? A scalar multiple of another vector. So one vector is a scalar multiple of the other. Okay, so we'll see, actually, well, that's what it would look like geometrically. So when it comes time for the actual, an example of that, let me just throw one together real fast. So we have x, y, and z for one line. And then for the second line, x, y, and z. It's not about the point. The point could be anything, 1, 0, 5, and 3, 2, -1. But when it comes time for the direction vector, say we have 3, 5, -1, and all these have t's on them. So this guy's direction vector is 3, 5, -1, and it's I, j, and k components. If this guy is, let's say, -6 and -10 and +2 with t's on them, these 2 direction vectors are scalar multiples, and it's a visual thing. You should just be able to look at it and see, wow, from that I component to the other I component, I multiply by some constant k. If it's that same constant with the j component and the same constant with the k component, then yes, that vector, call this vector v2 and this vector v1. V2 is 2 times v1. It's a visual thing. You should just be able to look at it and see. So that's a quick check. Just look at focus on the direction vectors. If one is a multiple of the other, sorry, that's a lie. Why you guys let me write that? If one is a multiple of the other, then yes, they are parallel lines. Okay. Great. So you'll be able to tell simply by doing a visual based on the direction vectors only, not about the point, but the direction vectors. Is that okay? The other ways that the lines can interact are more complicated. Let me, I'll tell you what, let me, yeah, sorry, I gotta erase all this. Okay. So, the lines can intersect, but there won't be a quick way to tell that. We have a quick way to tell when the lines are parallel, but there's not a quick way to tell when the 2 lines are going to intersect. And so, to keep the lines separate, it's good to use a different letter for your parameter. And so, in that example I just did, I had my parameter being t for both of them. That's not normally the best thing to do because the parameters can vary, and so I shouldn't use the same letter for them. So from here on out, I'll use one parameter t for one line and some other parameter s for another line, just to let you know that they don't have to be the same t at the same time. And so it's possible to see. I'll show you an example of lines that intersect, and you won't be able to just eyeball it and tell. For parallels, you can just eyeball it and tell. Intersecting, you can't. We'll show the mechanics of what happens behind the scenes to know whether they intersect. Now, there's a third option for lines, and it's basically it's not intersecting and it's not parallel. So if they're parallel, there's some plane that goes through both of them. But when you have the last option, there isn't a plane that would contain both lines, and so it's called being skew. It's like taking two lines that aren't on the same plane, then that's what it means to be skewed. The picture will do it no justice. The picture that I'm about to show you does it no justice. But it's just, they're not intersecting, and they're not parallel. Okay? And so, non-intersecting and not parallel, there's no value of t and s that would make them have the same, so they're not intersecting. And their direction vectors aren't, I shouldn't say their direction vectors aren't parallel, but I should say there's, aren't scalar multiples of each other. And if that's the case, then they're called skewed. That picture does us no justice, but just take two writing utensils and just hold them up in a way that where they're on different planes and they aren't going in the same direction, and then just picture that being extended out in all directions. That'll give you a visual of what skew lines look like. But still, telling that just by the parametric equations, it's going to be some algebra we need to do for our second and third case for B and C. No algebra really, it's just a visual for A. And so we're going to have one example of intersecting lines and one example of skew lines on the next two slides. Any questions about this particular slide, about this setup here? Okay. So these are the three ways that these two lines can interact. So here's two lines. One has the parameter t, the other has the parameter s. Called one line L1, the other line L2. And we're going to see how can we tell algebraically behind the scenes that these guys are one of these three types. And they have to end up as one of these three types. First off, right away, they are not parallel. And it's a visual. The direction vector for the first one is -1, 3, -4. And the direction vector for the second one is 2, -4, 1. There's not a number that you multiply by to get the other. It needs to be a single number that you multiply one vector by to get the other. And so that's not the case. So they're not parallel. Okay. Because V1 is not some constant times V2. -1, 3, -4 is not some constant times 2, -4, 1. No way to do that. All right, so here's what you got to do then. To decide what's going on between the other two cases. If they're going to intersect, it has to be true that the x's are the same. If I have this point, x, y, z, where the lines intersect, then they have to share the same x coordinate, the same y coordinate, and the same z coordinate. Perhaps for different parameters, t and s, but it has to be true. So if they have a chance to intersect, it must be true that 3 minus t is 8 plus 2s. If they have a chance to intersect. And so what that does is give me some relationship between the t and the s. It doesn't tell me exactly what they are, but it will be true if we set it up and solve for one of them that we can get some relationship in terms of the other one. So if we solve for t, we say, okay, subtract the 3 over and then change all the signs. It is true that t is -5 minus 2s. True statement. If the x's are to equal each other. But nothing special about x's, we can just move quickly to the y's, and that same relationship has to be true. Because at the same time my x is going to be equal, my y's will be equal as well. Same time, same parameter, same t, and same s. And so I take and set the y's equal to each other. So it should be true at the same parameter values that 5 plus 3t is -6 minus 4s. And I now know how t and s are related, so I can substitute that relationship in. Every time I see a t, I can replace it with -5 minus 2s. So that gives me an equation only in s, and that will nail down exactly what s needs to be so that my x and y are matching. So I have, what, -15 and a -6s, and then solve for s by adding the 6s over and adding the 6 over. You end up with -2s is 4, and then so s has to be -2. It will always be some nice integer value, but I set it up this time to be that way. If the x's and y's are to equal at the same instant, then the parameter for s needs to be -2, and I can quickly go find out what the parameter for t is. The parameter value of t is because I can just plug in the fact that s is -2, and I get -1 for the t. This ensures that x and y are the same. When s is negative 2 and when t is negative 1, the x will be 4 and the y will be 2 for both of those lines. The question at hand is, what about the z? And that's how these last two options will differentiate themselves from each other. We'll always be able to do that algebra that we just did here for these two levels. When it comes time for z, taking those parameter values for s and t, they have to be the same. And for intersecting lines, they will be, but for skew lines, they won't be. That's it. So I think this is the one where they intersect. When t is negative 1, what do we get for z value? Is that 3? And then for the other guy, when s is negative 2, we get a z value of 3 as well. So we need to check and make sure the z values are the same at that same instant. And it is true that they are the same. So I even know the point now, because I went through the work, the x is a 4, the y is a 2, and now the z is a 3. That's the point where they intersect, and I'm done with that question. I'm gonna go quickly through the first part of the next example because the algebra is the same, and I'm going to advance on to this last level here, the z check, and show you how when they're skewed, you'll get your x and y can be the same at that instant, but your z will be something else. So so you can get the visual of what's going on. It's possible for the x and y to be the same, but the z to be something else. That means they're on, at that instant in time, they're not on the same plane. They're not the same. They're not intersecting at that point. They're on different planes. And so so quickly go through this. This is two different lines. Okay, than what we had before. And what's going to happen is set the x is equal, set the y is equal. We'll end up with an s value and a t value. You can always do that. But then when it comes time for the z, they will not equal. My x's will be, let's see, my x's will be 1, and my y's will be negative 2. No. Yeah. My x's will be 1, my y will be negative 2, but my z's aren't the same. Okay, on the one hand, my z is negative 36, and on the other hand, my z is 0. So when this happens, I say that the lines are skewed. Okay? At that particular instant in time, your x and y are syncing up, but your z is not. So those lines are skewed. That's a typical question you might see. Here's two lines. Tell me if they're parallel, skew, or intersecting. We've seen how to do that for each of these three types. Okay, that was kind of fast, that second one, but you get the point. Any questions? All right, so that's our extent about what we need for lines. Just know what you need to get the equation of the line and know how to set it up. You need a point and you need a direction vector. And so there's other questions we can ask. This isn't the extent of types of questions, but in the end, just remember what you need. And as long as you can go and get those two things, then you'll be able to find the equation of the line. All right, so then we move to planes, and the setup is similar. Planes, we're going to need two things as well. And it's going to start off that, yes, we're going to need a point that's on the plane. And the other defining factor for a plane will be the normal vector to the plane. When you have a plane in space, there's infinitely many vectors in the plane, but up to a constant at least, there'll be one vector that is normal to the plane. I can scale that vector and make it longer and shorter. I can make it go on the opposite. I can make it. I can make it so that at a particular point it goes from that point out one way or from that point out another way. But when we say normal or when we say orthogonal to the plane, that means that when it intersects the plane, it's intersecting the plane at a right angle. And so we're going to change our verbiage. Instead of saying orthogonal, we're going to say it's normal to the plane. These are the two things you need. And the battle is going to be how to find the normal vector. It's not going to be trouble to find a point that's on the plane. Most times you'll be given a point that's on the plane. The hard part is going to be how do you find the normal vector to the plane. So once again, here's the derivation. You don't have to follow, but I need to be able to explain why the equation looks like what it looks like. And so it's the same kind of setup. Random point out in space, x naught, y naught, z naught, known to be on the plane. Tie that down to the origin, get a vector from the origin to that point, call that r naught, that's your initial position. Take a random other point that's on the plane, call it x, y, z. Take the vector that goes from the origin to that point, that's your position vector. All points on the plane will satisfy an equation in this x, y, and z. And whenever you see r as a vector, in your mind translate to mean that's my position vector. We're going to move from lines and planes into curves in space. And it's the same idea. Whenever you see an r, it's called, it's meant to be a position vector. That'll tell you any generic point that's on the plane, on the line, on the curve. Okay? And then I connect them with a vector. And then I have the subtraction vector whenever I have two vectors. So the vector that connects those two will be in some relationship to the two vectors. In this order, it's going to be r minus r naught if I want to go from the point p naught to the point p. And then generically, if you're trying to draw a plane, most people just end up drawing a parallelogram, and it's meant to be that it extends out forever in all directions. And so what I need is a normal vector to the plane. I need a plane that comes and intersects at a right angle. I need a vector that comes and intersects this plane at a right angle. And we'll call the normal vector n. It'll have I, j, and k components A, B, C. Okay. So we go, just like we did with the line, let's break down the I, j, and k components of all these vectors. R naught is from the origin to the known point, so that's x naught minus nothing, and y naught minus nothing, and z naught minus nothing. R is from the generic point in the plane and the origin, so x minus nothing, and y minus nothing, and z minus nothing. The vector r minus r naught is the subtraction of r's coordinates minus r naught's coordinates, so x minus x naught, and y minus y naught, and z minus z naught. And then the normal vector is just ABC. And what's the tie-in factor that we need is these guys need to be orthogonal to each other. The blue vector from P naught to P and the red vector, the normal vector, have to be orthogonal. So what's so special about orthogonal vectors? It means that they meet at this right angle, and how can you tell algebraically if two vectors are orthogonal? Because dot product is 0. Okay, so let's take these two vectors and dot them. That's the general idea of how we go and get the equation of the plane. This itself can be thought of as the equation for the plane. We normally don't do it like that. It's called the vector equation. Take the normal vector and dot it with the p naught p vector. And so you can use this to get the equation of the plane. But just like with the lines, that's not the normal way to do it. When we really want something, when somebody asks you for the equation of the plane, there's a certain way it looks. We've seen planes before, some constant times x plus some constant times y plus some other constant times z equal to some other kind of constant. And that's what we need. To get that, let's look exactly what this means. Dot in with r and dot in with r naught and set them equal to each other. Or go with the other version of and dot in with p and set that equal to 0. So dotting in with p naught p vector, you get exactly component-wise. I take these guys here and I multiply them by these guys here. A times x minus x naught, b times y minus y naught, c times z minus z naught, and that needs to be equal to 0. Dot product between those two guys. Distribute across, and you have exactly what you need. We have ax and by and cz, and then a bunch of constants. A times x naught and b times y naught and c times z naught. And so this can be thought of as the equation as well, written in this format. Remember what you know. You'll have these guys on hand, and you just plug them into that formula. Not the standard way, but it works. It is the equation. It's real easy to do. And in most cases, you probably go right to that. If you had A, B, and C, and if you had x naught, y naught, z naught, perfect. Just plug right into this. But in most instances, we'll be looking for the third form here, where I go and distribute the A across, distribute the B across, distribute the C across, and then the normal type of equation that we'll be looking for is some A times x, some B times y, some C times z, and then some constant. This guy here is just some constant. These are known things. A, B, C, X naught, Y naught, Z naught are all known, so you can plug them in and figure out exactly what it is. And whether you want the D on the left-hand side or the right-hand side, it depends on what the person wants. There's nothing wrong with it being set equal to 0. In most places, you might see the D on the other side, but either way it goes, this is the standard way we're going to have for our equation. Officially, the name of it is the linear equation of the plane. I think I end up liking the D on the other side, but whatever. It's just a personal preference. It's not a standard way of writing it. Okay? So it's okay if you don't understand the derivation. I want you to be able to jump from I need you to know what you need, and then know what to do with it, and then the end result. Okay? And 99% of the time, it's not a mystery what the point is. It's a mystery what the normal vector is. So let's see a couple examples of you finding the equation of the plane. If there are any questions. Question, yes, hi.
Could we just cross the two vectors to make a normal vector?
Exactly. So that's what's going to happen in most cases, right? A vector, I need to cross two vectors that are in the plane, though, to get the normal vector. Remember what the cross product is. Cross product is a vector that's orthogonal to the two vectors that you're crossing. So in most instances, I'll end up with getting two vectors that are in the plane and cross them to get the normal vector. Okay? If you cross in one direction, you get the normal vector pointing up through the plane. If you cross in the other direction, you get the normal vector pointing down through the plane. And so either way is fine. That's exactly it. And so here's two lines out in space. Okay, these are the two lines that we had before that intersected in the point. So we know there is a plane that contains these two lines. Our job is to find that plane. Okay, hidden inside these equations is lots of information, right? Each one of these equations has a point and a direction vector. And for these guys to end up on the same plane, I immediately have in front of me 2 points and 2 direction vectors in the plane. I have 2 vectors in the plane. I have 2 points on the plane. I have a plethora of information, and I just need to know what to do with it. And so in order to find the equation of the plane, I know I need a point, and I know I need a vector that's normal to the plane. And I have a lot of stuff with me. When it comes time for the point, there are 2 points right in front of me. 3, 5, -1, 8, -6, 5. Just pick one, it doesn't matter. That'll be the point that you'll use. And then when it comes time for the vector, the normal vector, we don't have it. We do have 2 vectors, though, that are in the plane. The direction vector for the first line and the direction vector for the second line, they are in the plane. They are not the normal vector to the plane, but as he said, just cross them. And that will give you the normal vector to the plane. Up to a constant, you know what I mean? So cross those 2 vectors, and you have part B, and then you'll put those 2 together to give the answer. All right, so go ahead, you do it. I'd like for you to cross these 2 vectors. I have it written as the U cross the V. If you started working out already and you cross them the other way, that's fine. You'll still get the same answer I get. Our plane equations will differ by a negative sign. So U cross V is the opposite of V cross U, right? So cross them. What does that mean? That means make up this matrix that has the first row of vectors. It's kind of strange. And the second and third row are actually numbers. And however you're comfortable doing this cross product, you do it. And then we're looking for the result. The result of this cross product is a normal vector to the plane. There's actually many of these, so I say a normal vectors. And so let's what do we get? What's the I component of this vector? 3 minus 16. So it's going to be a 3 minus a 16. So it's going to be a 13. The j component of this vector, crossing out j's row in column, you'll have -1 minus a -8. But then don't forget, with the j component, you have to associate this negative sign to it. And then when it comes time for the k component, you'll have a +4 minus a 6. So we get a -13 for our I component. Looks like a -7 for our j component. And yeah, -2 for our k component. If you happen to recognize that your cross product has some relate the ij and k version of your the ij and k components of your cross product, if you happen to notice that they all have something in common, you can factor that out. All that's doing is making the cross product vector have a different length. It's still normal, and when it comes time to dealing, remember this is supposed to be your a, b, and c. That is that's here, and if you have to go do calculations with the a, b, and c, you want the most simple version of it, and so what you can do is factor out a negative if you wanted to, or sometimes you'll notice everything is even, so factor out a 2, or everything's a multiple of 3, so factor out a 3. Do that. It just makes your life easier when it comes time to now to go do calculations with the a, b, and c. Okay. So here, and you already know what the answer looks like, right? The answer to what a plane looks like is ax. The equation of a plane is ax plus by plus cz plus something equals to 0. And you already know the a, the b, and the c. The x, y, and z are the variables. The only mystery to you, once you go out and get your a, b, and c, the only mystery to you is what the d is. Okay, so you have part of your answer already. It looks like -13x and -7y and -2z, if you want to go with that version, or the positive version of all those. That works too. And so now we just need to know what d is, and I think the best way to find d is to actually take this particular equation right now and pick either of these, either of these points should satisfy the equation. So pick one and plug them in as x, y, and z, and that'll tell you what d is. You don't have to do it this way, it's just the way I like to do it. So -13 times a 3, and -7 times a 5, and -2 times a -1 should be, when I add it to d, I should get 0. Okay, taking that particular point, 3, 5, -1. And so I end up with a -39 and a -35 and a positive 2, plus the d should be 0. So d is 72. Oh, this gives me a -72 plus the d is a 0. So d better be 72. So I take exactly this equation and I throw in the 72 and I'm all done. The answer to the question would be, or one version of the answer would be -13x minus 7y minus 2z plus the 72 equals to 0. And if you notice that all the answers on the multiple choice or the answer in the back has the 72 on the other side, then just do that. And it would probably look like 13x plus 7y plus 2z is equal to 72. It'd probably look like that. And some people prefer this version of an equation of a plane to the other one. I don't know. Okay? So go get the normal vector, and 9 times out of 10, you get the normal vector is about you finding 2 vectors in the plane and crossing them. The normal vector is orthogonal to every vector in the plane, in particular, orthogonal to any 2 vectors that you can go and find in the plane. Question, yes?
If you were to have this question on the exam, wouldn't it be possible that one of the answers would be like a scalar multiple of whatever you actually get?
Yeah, you'll have A through H. I get 8 choices, and you'll be able to tell, what I did. If I give this answer, say the one that's on the bottom, okay, but then that one times a -2 is what you ended up getting. You'll be able to know. Good question. Yeah. Let's see another way the problem can come at you. Here's 3 points. That's enough to define a plane as well. We just saw that 2 lines in the plane is enough to define the plane. 3 points is the general basic thing you need to define a plane. Okay? And so we need to go and get the equation of the plane that passes through these 3 points. Remember what we need? We need a point and the normal vector. So pick any of these 3 points and you got your point. Call them P, Q, and R. So pick P probably, that's the point you would pick. And then when it comes time to find the normal vector to the plane, it's about you going out and getting two vectors, any two vectors, and crossing them. You have a bunch of points, not vectors, points. Okay, for me, parentheses, that's the coordinates of a point, and V brace, that's the way I use my notation for a vector. Some people, they do their vectors with parentheses. That's bad. Okay, I need two vectors. Suggestions. I have 3 points. I need to turn those 3 points into two vectors. Go. How?
PQ and PR.
PQ and PR, I like that. So get the vector that goes from P to Q. Get the vector that goes from P to R. Those are two vectors. Or any order of those would work. You don't care which, just as long as you get two vectors. They'll all end up in the same answer, maybe scalar or multiple. If you chose QP and QR, Q is your anchor point. If you choose P as your anchor point, or if you choose R as your anchor point, it all works. Okay? So I'm going to do PQ and PR. PQ, remember, 2 points out in space. The vector goes from one point to the other. Take the terminal, subtract the initial coordinates. So 3 minus 1 and 2 minus 1 and 1 minus 3, that's my PQ vector. 2, 0, negative 2. My PR vector would be a negative 2, a negative 4, and a negative 1. Yeah. I now have two vectors in the plane. Great. And I need the normal vector to the plane, so I cross them. Not that bad. So we have the I, J, and K components of the cross product. After a while, you get to the point where you won't need to write it all out like this, but here it is. Cross out the I row, cross out the I column, you have the little 2 by 2 determinant, 0, negative 2, and negative 4, negative 1. Cross out the J row, cross out the J column, you have the little 2 by 2 determinant, 2 and negative 2, and negative 2 and negative 1. Don't forget the fact that you have to change the sign on that J component, and then finally cross out the K row and cross out the K column, and you have the little 2 by 2 determinant, 2 and 0, and negative 2 and negative 4. So what is your cross product between those two vectors? It's going to be a negative 8 for the I component. And then a negative 2, take away 4, so a negative 6, but then don't forget to change the sign, so positive 6 for the J component. And then a negative 8 for the K component. And you recognize these guys share something in common. Let me shorten that vector. Let me use a different vector, still orthogonal to both these vectors. I'm still normal to the plane, but let me just change the length of it to make my calculations easier. I don't want to deal with 8, 6, and 8. I don't want to deal with those. I'd rather deal with 4, 3, and 4. So I'm going to factor out a negative 2. That's okay with you? And call it 4, 3, negative, 4, negative 3, and 4. Are we okay with that? Little calculations. And that's what I'd rather use. It's kind of like the lowest terms of that and the easiest thing. Because what I'm going to do is now, this is my A, B, and C. What do I do with the A, B, and C? I take the A, B, and C, I plug them in. I already know what my answer looks like. My answer should be 4x minus 3y plus 4z. I just don't know what this constant is. So I go and get it. I take x equals 1 and y equals 2 and z equals 3. One of these three guys, I take P, I plug it in, and I can get what D is. That's it. 4 take away 6 plus 12. Not bad at all. So D is 10. Plus the D is 0, so D is negative 10. Great, so I'm done. I know the answer to the question. It's 4x minus 3y plus 4z minus 10 is 0. And if you don't see exactly that answer, don't panic. Maybe yours is a multiple of that. Maybe you can factor something out. I try to have the answers in lowest terms. So if you had chosen the original negative 8, 6, and negative 8, then you would have had, negative 2 times this equation. Questions about this? Yes?
When you're picking your two vectors, you always have to make sure that the anchor point is the same. Like, you could
You don't even have to do that. You can do P, Q, and R. Any combination is great. There's infinitely many vectors in this plane. It's your job to get 2 of them. And so any 2 you can get, go get them. You end up with the same answer. Maybe some scalar multiple different on the answer. But it should reduce down to the answer. That's going to be the one that I would want to put. Not bad, right? Okay. Great. Now, when it comes to planes and how they interact with each other, there's only 2 options. The planes are either parallel or they are going to intersect. When they intersect, it'll be in a line, not in a point. Planes are parallel. Well, how do you know whether the planes are going to be parallel? If your planes are parallel, then it's about the fact that the normal vector to the one plane, a normal vector to the one plane, and a normal vector to the other plane, they won't be exactly the same, but they should be scalar multiples of each other. So whether they're parallel is the same visual. Here's an example of parallel planes. 4x minus 5y plus 3z equals 10, and negative 16x plus 20y minus 12z equals negative 40. These, oh, not sorry, something other than that, equals 15. Sorry. That would be the same plane, I'm sorry. What I had at first was the same plane. These are 2 different planes that are parallel. Their direction vectors, direction of their normal vectors, are scalar multiples of each other. When you're parallel, your normal vectors are scalar multiples. It's a visual thing. Okay? You should be able to look at the normal vectors and just eyeball it and know, yeah, I just take this guy and multiply by negative 4. That's how I get this other guy. That's all it is. Okay? But the intersection is more complicated. Okay? If they're not parallel, they're going to intersect. And there's a lot to be said about these planes. So let me show you how you can sort of figure that out algebraically. Not just the fact that they are intersecting, but you'll be able to find the equation of that line that they intersect in. Okay. You'll be able to tell the angle between the planes as well. Okay, let's start with, here's 2 equations, and I can look at that and know for sure that they are not parallel. I can eyeball it, right? These planes are not parallel. They're going to intersect in a line. So how can I know a way to represent that line? How can I find the line? What we're going to do is algebra. We're just going to eliminate a parameter, basically. So if I take 2 times the first equation and add it to the second equation, I'll end up losing my z, not my x. I'll end up losing my z. I'll end up with, adding these together, I'll end up with 4x minus y equals to 0. Yeah. My z's have been eliminated. Okay, 4x minus y equals to 0 is what I get from that. And that gives me a relationship between y and x. On the line, it will be true that y has to be 4x. Whatever I get for y, or whatever I get for x, I have to times it by 4 to get the y. I can take that information back into either of the original equations, and I can get how z relates to x. So if I know that y is 4x, then I can go back to the first equation and plug a 4x in. If I plug a 4x into the first equation, I'll have x minus 8x plus the z is 0. So I have that z is 7x. If y is 4x and z is 7x, then it must be true that I can now write the equation of the line. Let x be the parameter. I mean, don't call it x though, just call it t. But then right away you'll know the y and the z. The line won't always contain the origin like this one does. Okay, generally there's more to it. Generally there'll be something other than 0 here. This is a special case where I have them set equal to 0. Generally it'll be like y is 4x plus some 7, and then you take that in, and you get that the z is 7x plus some 11, or you know what I mean. So generally that's the case. But here, this line that we have as the intersection, it just happens to go through the origin, and the equation of that line is x is t, y is 4t, and z is 7t. And that's our answer to the question. If you want to think about it like this, it goes through the origin and has direction 1, 4, 7. In general, as long as these guys aren't both 0, then you're going to be fine. If they're both 0, then this will always happen. And so it won't be always the case that both of these guys are 0. And you'll have some point other than the origin that'll come out. You know, there's still an xbt though. You'll have y as a function of x and z as a function of x. And then x is free to be anything you want it to be. X is your parameter. You will still have x equal t, but the y and the z will have something other than 0 there. Is there questions about that? That's the equation of the line of the intersection between these two planes. Okay. And we can find the angle between the planes. It's true that the angle between the normal vectors is the same as the angle between the planes. Just take a book or take your notebook, have one part be the one plane, the other part be the other plane, and think about the normal vectors to each of those. And then remember, when you're trying to find the angle between two vectors, just make the initial points one on top of the other, and the angle between the normals will be the same as the angle between the planes. And so if you're trying to find the angle between two planes, go right to the normal vector. And so now remember, if I take and extend this out, both planes, I extend them out, I'll have an acute angle and an obtuse angle. And what I'm talking about is the acute angle, so I force it to be a positive cosine. This here is an absolute value sign. This just makes sure that this is, when we say the angle, we mean the acute angle between two planes. Okay? We know the formula to how to find the angle, the cosine of the angle. And so with our equations, we just take the ijk, the ABC, and of each of these guys, and they become the ij and k of the normal vectors. And then we plug into this formula. The magnitude of one is √6, the magnitude of the other is √17. It's not going to be an angle I know, but when I do the dot product, I get a -6. I can at least say what the cosine of it is. And then when it comes time, if I have to nail down what the angle is, I'll just say it's the cosine inverse of that. That's all. It ends up being about 45 degrees, but I'd rather you just write it as cosine inverse of that number. Okay. And we'll stop right there. I'll see you guys on Friday, and we'll talk about how to find the distance between a point and a plane. And that'll be it for this section. Remember, you have your first homework assignment due on Friday. Come early so that you can get it turned in and be able to listen to the lecture. If you come late, still come down and turn it in. It'll be separated by recitation. Make sure you know your recitation number and you put it on the homework. All right, see you Friday.